Hello everyone, my name is Nidhi Chauhan and I'm assistant professor in Gyan School of Pharmacy that is a part of the Suresh University chapter. So today we are going this topic that is a cycloalkene that comes in the pharmaceutical and chemistry section, and here we are going to discuss the cycloalkene. Let's start the learning objective. So here we are going to study about the isomerism in cycloalkane, what type of cycloalkane is happening in this cycloalkanes, and to study and also we are going to study about the methods of preparation of cycloalkanes and learn about the chemical reaction of cycloalkanes. And the student outcome is that they are going to know about the system trans cycloalkane. That means the isomerism that is happening in the cycloalkane is a system trans, and we are going to study this system trans. And we are also going to know about preparation method of cycloalkanes. Means here we are also going to discuss about this method, how the cycloalkanes are prepared from the various methods, and also we are going to know about the chemical reactions, but how the chemical reactions are happening in the cycloalkanes, or you can say that how the cycloalkanes are forming different products from it, and this all we are going to study in this today's lecture. So the first is the isomer, second is the method of preparation, and the third is the chemical reactions. First is the cis-trans isomerism in cycloalkane. So because of this cyclic structure, the cycloalkanes have two phases when viewed edge-on, a top phase and a bottom phase. As a result, cycloisomerism is possible in substituted alkanes, cycloalkanes. So, because as we know that cycloalkanes means the alkanes which are present in a cyclic structure, means they are present in a closed ring. So here, because of their cyclic structure, because they are having a cyclic structure, they have the two phases. Uh, Two phases when viewed edge on a top phase, one is your top phase and one is your bottom phase, and as a result, chemical isomerism is possible in substituted cycloalkane. So in this isomerism, as you all know, what is isomerism is that isomerism in which your molecular formula is same but the structure formula is different. And there are two type of structural isomerism and the stereoisomerism. So here the isomerism is possible in substituted cycloalkane. So here the isomerism is possible in the substituted cycloalkane, means on that cycloalkanes in which the H hydrogen is substituted with some other atom. So for example, here given there are two different 1,2-dimethyl cyclopropane isomer, one with the 2-methyl group on the face, same face of the ring, and one with the methyl group on opposite face. So here, as you can see in the figure, that there are two different 1,2-dimethyl cyclopropane isomers, one with the 2-methyl group on the same face of the ring and one with the methyl group on the opposite face. So both isomers are stable compounds and neither can be converted into the other without breaking or reforming a chemical bond. So here the cycloalkane cannot be break and it cannot be reformed. So here the result of the isomerism. Here, the result of the isomerism is possible in the substituted cycloalkane. For example, we are given the two isomers of this 1,2-dimethyl cyclopropane, and one is a cis and the second is a trans. So in your one is having the 2-methyl group on the same face of the ring, means they are present on the same side of the molecule, means of one of the this molecule, this 1,2-dimethyl cyclopropane, and the two methyl groups that are present on the different side of the this ring. The cycloalkane means on the opposite side of faces. So both isomers are stable compounds. So both of them are the stable compound. Both the isomers are the stable compound. But but in this case, neither can be converted into other. In this case, if they are not converted to another molecule, or they cannot be reformed, or they cannot be baked. So here, these chemical conduits are not cannot be or baked and or reformed. So these two figures here, figure 4.2, there are two different 1,2-dimethyl cyclopropane isomers and one with the methyl group on the same face of the ring, that is your cis, which are the methyl group that is present on the same side of the molecule of, or the same face of the ring, that is known as your cis, and the other with the methyl group that is present on the opposite face. So that is known as your trans. And the two isomers do not interconvert. They cannot be interconverted because here the bond between this carbon, they are this cannot be interconverted, or they cannot be broken, or they cannot be reformed. Again, this cis-trans isomerism. Cis-trans isomerism, this means they are the two molecules, the two atoms that are present on a molecule that is on the same side of the molecule. But we have already studied this isomerism. In that, we have studied that this cis and trans, they are present on the double bond, geometrical isomers. These are the type of the geometrical isomerism, and in this, the two uh, carbon and connected on the alkene, means they are connected on the double bond. So on that double bond, the one carbon is having the two atoms connect bonded to each, and if the two molecules that are having means if the two molecules, that is alkyl group or any other group that is attached to the two carbon atom, are on the same side, then that is your cis isomerism. And if they are present on the different side, then that is your trans, then that is your trans isomerism. And in this cis in this cis in the cis, you can see that in the cis, as you can all in the cis, we can also say that if the hydrogens that are present on the same side of the this ring, same side of the ring, then this is the cis isomerism. And if it is present on the different side of this ring or the double bond, then that is your trans isomerism. So here they are, this type of isomerism, this cis-trans isomerism is shown in the cycloalkanes, and because of the cyclic uh, structures, these cycloalkanes have the two phase, as we can view it on the edge. So here the top phase and on the bottom phase. So top phase and the bottom phase. So the two phase we can see in the cycloalkane. That is why this cis and trans isomers are occurring in this cycloalkanes, and due to which as a result the isomerism is possible and substituted, not in the same cycloalkane. Means if for example we have taken here propane, so in the propane, cyclopropane, the isomerism will not be possible. This isomerism is not be possible in that in this propane, because all are having the hydrogen atom. But if the two hydrogens are substituted, by the alkyl group or any other group, any other function group, and if they are present on the two carbon of the same side, then they are showing this isomerism, this trans isomerism. And here the example is taken as 1,2-dimethyl cyclopropane. So in the 1,2-dicyclopropane, the two hydrogens on the two carbon atom are substituted by this alkyl groups. So by this methyl groups. So here you can see the structure of this 1,2-dimethyl cyclopropane. Why it is called 1,2-dimethyl cyclopropane? Because we are starting the counting from here, 1, 2, 3. So 3, it is 3 and it is in circle, it is in ring, then it is your cyclopropane. And here you can see here this carbon is having the two hydrogen. This carbon is also having the two hydrogen. This is also having the two hydrogen. Then it is called the cyclopropane. But here the two hydrogens on this place and on this place. The two hydrogens has been replaced by this methyl group. So this from this methyl group it has been replaced, and here the dimethyl. So here written 1,2-dimethyl cyclopropane. So here it is written 1,2-dimethyl because two methyl groups are attached to this carbon atom. So here the two carbon atoms are attached to this carbon atom. That is why it is known as 1,2-dimethyl cyclopropane. So there are two different. Here you can see there are two different. This is also the dimethyl cyclopropane, and this is also the dimethyl cyclopropane, 1,2-dimethyl cyclopropane. So here you will see that this is your CH3, this is your CH3, and they are present on the same side. And in this structure of this 1,2-dimethyl cyclopropane, you can see they are on the different side. They are on the different side. One CH3 is this side and one CH3 is this side. And H is on this side and H is on that side. So here you can, that is why it is written that if the two methyl groups are on the same side, if the two methyl group are on the same face of the ring, then it is known as your cis 1,2-dimethyl cyclopropane. And if this dimethyls are on the different or on the opposite face or are on the opposite face, then it is your trans 1,2-dimethyl cyclopropane. So both isomerism are stable compound and neither can be converted into the other without breaking or reforming chemical bond. If you have to convert it, then you have to break this bond. अगर आपको reform convert करना है, then you have to break this bond, and firstly you have to break this single bond. And in that case also, when these are connected to the double bond carbon atoms, then also they are neither can be converted nor can be they are they are neither can be converted into another without breaking and reforming chemical bond. These are the two isomerism that comes in your geometrical isomerism, and these two isomerism are shown in the cycloalkanes, in the substituted cycloalkanes, not in the normal cycloalkanes. And here this is of two types, that is the cis and the trans. And on the cis, they should be on the same, the two methyl or the two substituted function group should be on the same side of the ring. And if that is known as your cis if they are on the same side, and if they are on the different side, then they are the trans isomerism. So in the figure, there are two different 1,2-dicyclopropane isomers, one with methyl group on the same face of the ring, that is your cis, and the other with the methyl group on the opposite face of the ring, that is your trans. And two isomerisms do not interconvert. They cannot be interconverted. Next is your, unlike the constitutional isomerism, butane and isobutane, which have their atom connected in a different order, the 1,2-dimethyl cyclopropane have the same order of connection but differ in the spatial orientation of the atom. Such compounds with atoms connected in the same order but different in three-dimensional orientation are called stereochemical isomerism or stereoisomerism, and more generally the term stereochemistry is used to refer to the three-dimensional aspect of chemical structure and reactivity. So here, unlike the constitutional isomerism, butane and isomerism, which have their atom connected in a different order. So here the example is given in this. You can see that the constitutional isomerism, that is your different connection between the atoms. So there is a different connection in your atom. Here you can see this CH3, CH, CH3, CH3, and CH3, CH2, CH2, CH3. So here the butane and isobutane. This is your isobutane and that is your butane. So which have their atom connected in a different order. These are the two having connected. They are connected. That means their molecular formula is same, but their structure is different. As you can see, there are four carbons in the isobutane, also in the butane also, and they are having 10 hydrogen atoms present. And here also in the butane also the 10 hydrogen atoms are present. So this is your isomerism, in which the molecular formula is same, but structure is different. So in this case, this is the isomerism. Yeah, okay. So there are the different connections between the atom. In consecutional isomerism, you can see the different connections between the atom, and which have the atom connected in a different order, and the 2,1,2-dimethyl cyclopropane have the same order of connection but differ in the spatial arrangement of the atom. Here, but in case of your this cis-trans isomerism of the cycloalkene, you can see here that in this case, this structure is same. Structure is same of the cycloalkene, but the difference is that they are connected, or they are differ in their spatial orientation of the atom. So as you can see, but so the difference between this constitutional and the stereoisomerism, that in the constitutional isomerism there are different connections between the atoms. These are atoms that are connected, they are differently connected. Okay, but in the case of stereoisomerism, the connection is same, but they are arranged, but they are different in the arrangement of the atom, or you can say they are different, they are having the different three-dimensional geometry. So their three-dimensional geometry is different. So here in this case, so the such compounds with atoms connected in a same order but differing in their three-dimensional orientation are called stereochemical isomerism or stereoisomerism. So here the compounds that are showing, or they are in that, if their atoms are connected in the same order but they are differ in their three-dimensional orientation, or you can say a spatial arrangement, then they are known as your stereochemical isomers, stereochemical isomers or stereoisomers. So more generally, the term stereochemistry is used to refer to the three-dimensional aspects of chemical structure and reactivity. The term stereochemistry is used to refer to the three-dimensional aspects of chemical structure and reactivity. So here you can see, unlike the constitutional, once again, unlike the constitutional isomers, butane and isobutane, which have the atom connected in a different order. So here you can see this is example is given, and this is your constitutional isomerism, and in this different connection between atoms are given. So here this both are the isomerism, and this is your butane, and this is your butane, and in this you can see that this CH3 is connected here on the CH, and here you can see this CH3 is connected to this CH2. So here the arrangement is different of these atoms. Connections are different between this atom. So, but they are having the same molecular formula, but different in their structure. Structure is different because of the connection between the atom. So here you can see they are having the 4 carbon atom. This is also having the 4 carbon atom, and this is having the 10 hydrogen atom, 3, 3, 6, 3, 9, and 1, 10. And in this case, you also see that this is also having the 10 hydrogen atom, 3, 3, 6, 7, 8, 9, 10. So this is the constitutional isomerism, and this is the stereoisomerism example. So in the stereoisomerism example, you can see these are having the same connections. These are having the same connection, as you can see on this carbon atom, this methyl group and this hydrogen atom, and on this carbon atom, this methyl group and this hydrogen atoms are connected. And you can see here on this there are two in the same, this also, this carbon, on this carbon atom, this both are connected, but their difference is that their connections are different. means their they not the connections, but their arrangement in the spatial differ in the spatial arrangement, or in the three-dimensional geometry is different there. So here you can see that they are turnable, means not turnable, means here this CH3 is here in this side, and this CH3 is this side. So the CH3 which is on the same side, as you can see, which is on the same side, that is your cis, and when this is on the different side, then this is your trans isomer. So in this you can see, and this is your stereoisomers, and this is known as stereoisomers, in which there is the connection, uh, that the atom that is connected to the to this to their carbon atoms, they are in the same order, but they are different in the, but means they are different in the three-dimensional geometry. Means they are their three dimension geometry is different here, and that isomerism are that isomers are known as stereo chemical isomers, or your stereoisomers. And the term stereochemistry is used to refer to the three-dimensional aspects of chemical structure and reactivity. So this is the term, this is the stereochemistry, this is the whole chemistry. In this we study the three-dimensional aspects of chemical structures, these are the chemical structures of the molecules and their reactivity. Also we study in the stereochemistry. So this is your stereochemistry. So this is the isomerism of your cyclopropane that are substituted. Means the isomerism, they are isomerism which are substituted, isomers that are shown in the substituted cycloalkanes. So this is an example also given here, that the 1,2-dimethyl cyclopropanes are member of the subclass of stereoisomerism called cis-trans isomers. The prefix cis is Latin word is on the same side, and the trans Latins across are used to distinguish between them. Cis-trans isomerism is a common occurrence in substituted cycloalkanes and in many cyclic biological molecules. So here the example is given is cyclobutane, and cyclobutane, no, the dimethyl cyclobutane, because cyclobutane does not show this isomerism. The substituted cyclobutane will show this isomerism. So here the 1,2-dimethyl cyclopropanes, these 1,2, this substituted cyclobutanes are showing, are, or you can say that these are the members of a subclass of the stereoisomerism. Means the stereoisomerism subclass is known as your cis-trans isomerism. So the subclass means the class of this stereoisomerism is your geometrical, and the geometrical part is your cis-trans isomerism. So the subclass of this 1,2-dimethyl cyclobutane, or the substituted cyclobutane, are a member of this subclass of stereoisomerism called your cis-trans isomerism. And the prefix is your cis. Here we use this cis. Cis has taken from the Latin word which means same side. On the same side means the molecules that are atoms, or the molecules that atoms, or the molecules that are having or that are connected or bonded to the same side of the atom, carbon atom. And the trans, and then trans is also taken from the Latin word that is your across, means they are on the different side, and these are used to distinguish between them. So these are used to distinguish between them, and the cis-trans isomerism is a common occurrence. It is a common occurrence in substituted cycloalkanes. These are this cis-trans isomerism occurs in the substituted cycloalkanes, and these are also present in many cyclic biological molecules. So here you will see this example is given here. This is your 1,3-dimethyl cyclobutane. Here you can see this 1, 2, 3, 4. That is why it is your cyclobutane. And if this CH3 is not present here, or in this CH3 place there is a hydrogen atom, then that is your normal cyclobutane. So here in place of your hydrogen, The CH3 groups are attached. That is why it is your cyclo 1,3-dimethyl, or you can say the substituted cyclobutane. So this is your cis, because you can see here that this CH3 and this CH3 are on the same side of this molecule of this cyclobutane. So this is on the same side of the cyclobutane. That is why this is your cis 1,3-dimethyl cyclobutane, and this is on the different side. This, you can see, this is another atoms that are attached to it. So this is your ethyl, this is your bromo, and this is your pentane. And if these are not substituted, then this is a normal cyclopentane, and this is not showing any isomerism. So here, if they are substituted, then they are showing this uh, isomerism. So here you can see on the first position, this bromo is on this side, and on the third position, this is on the different this is on the different side, or they are across or on the opposite face. So that is why this is your trans 1 bromo 3 ethyl cyclopentane. This is whole is your cis trans isomerism that is shown in your substituted cycloalkane. Next is the conformation of cycloalkanes. So the bond angle in straight chain alkane is normally 109.5 degrees. As you all know that in the case of alkane, the bond angle between the this hydrogen and this carbon bond, the bond angle is the 109.5 degree, and this is expected for a tetrahedral arrangement of bonds that are not restricted. So this bond angle that is shown here, that which is having 109.5 degree, is expected to having in the tetrahedral arrangement of bonds, so that are not restricted. As you can see, the cycloalkanes bond angle. So the cycloalkanes have different bond angles depending on their structure. So here you can see here, this is the bond angle that is shown in the alkane, in the this alkane, and these are the bond angle that are shown in this cycloalkanes. So here you can see the internal bond angle. So here you can see in this, the 60-degree angle is possible in this cycloalkane. In this butane, that is also showing the structure of the square. This is also showing that in this the bond angle will be 90 degree of all the sides. All the side it is showing that it is 90 degree. So in this case, it is showing that it is having 108 degree centigrade. Sorry, 108 degree. So this bond angle in this this is your 1, 2, 3, 4, 5 cyclopropane. So here the bond angle is your 108 degree. In this case, this is your cyclohexane. So in this, the bond angle will be 120 degree. So here the bond angle is equals to n minus 2 upon n into 180. So here n equals to number of carbon in the ring. So if there are three carbon in the ring, then if we apply this formula, then here 3 minus 2 upon 3. So here 3 minus 2 upon 1 upon 3, and 1 upon 3 equals to 3. We'll divide this 180, and here the 60 will come. So 60 into 1 equals to 60. And in the same case, here 90. So 4 minus 2 upon 4. 4 minus 2 equals to 2 upon 4. So 2 upon 4 means 1 upon 2, and 2 equals to 2 9 the 18. So 90 degrees. Okay, like this we will calculate the bond angle in this cycloalkanes. As we know that in the straight chain alkanes, the bond angle is always 109 degree, 9.5 degree, because they are having a tetrahedral arrangement of bond. And in this cycloalkane, there is there are different cycloalkanes. They are having the different structures present in this cycloalkane, and that is why their bond angle will differ. So for that, there is a formula, that is your bond angle equals to n minus 2 upon n into 180, where n equals to number of carbon in the ring, means how many carbons are present in the ring. For example, we have taken here hexane. So in the case of hexane, there are 6 carbon atoms. 6 minus 2 equals to 4. 4 upon 6 into 180. So 6 3 is 18. So 30 into your 2. So 30 into your 6 minus 2, 4. So 30 into your 4 equals to 180 degree. So here, like this, the bond angle will be calculated from this formula. However, when the carbon atom from part of a ring, the angle will be controlled by the requirement of the ring. So here, when the carbon atom form part of a ring, that the carbon atom is forming a part of a ring, the angle will be controlled by the requirement. Means the angle will be controlled by the ring. If the ring is in triangle shape, then the angle will be in angle will change into that form. And if it is in your butane, if it is cyclobutane, then the angle will again change. So here the angle will be controlled by the requirement. Means if the requirement, then it depends on the angle is depending on the requirement of the ring. So this is the conformation of your cycloalkane, that the bond angle in straight alkane is normally 109.5 degrees, and this is expected for a tetrahedral arrangement of bonds that are not restricted, and there is this alkane is present, and which it is showing the angle that is a 109.5 degree. And here the internal bond angles, here the internal bond angles is your 60, 90, 108 and 120. And here in this case, the bond angle the formula for calculating the bond angle in the cycloalkane is your bond angle equals to n minus 2 upon n into 180, where n is the number of carbon in the ring. However, when the carbon atom form part of a ring, the angle will be controlled by the requirement of the ring. So next is your method of preparation. So how the cycloalkanes are prepared, and how they are prepared with the help of the reagents or with the help of the catalyst that we are treating with the main element. So here first is your from dihalogen compound. So from the dihalogen compounds, means 2 halogen atoms are present here in this compound. So suitable 1,3 or 1,4 like dihalogen alkanes on treatment with sodium or zinc give corresponding cycloalkane. For example, CH3, CH2, CH2Br, CH2Br. So here 2 Br are present. That is why this compound is your dihalogen. So here given that if there is 1,3 or 1,4 dihalogen alkanes, or and we are treating with the sodium or zinc in the presence of the ethanol, that is your alcohol, and we are heating this, and there is a formation of this cyclopropane. As you can see in this example, this is your 1,3-dibromopropane. So this is your 1,3-dibromopropane, and in this 1,3-dibromopropane, why is this 1,3-dibromo? Because the counting will start from this 1, 2, 3. So on the first position and on the third position, there is the presence of bromo group. Bromo halogen is present. That is why we have written 1,3-dibromopropane. Propane is for your 1, 2, 3. 3 carbons are present. So its name is 1,3-dibromo. And here we are treating this 1,3 because this is your 1,3 and this is your dihalogen alkane, and we are treating this dibromopropane with your this sodium. So we are treating it with this sodium, or here we are treating it with the zinc. So here we are treating it with the zinc or with the sodium, and here we are getting this plus we are treating it with this ethanol in the presence of this alcohol. We are heating it, and there is a formation of this cyclopropane. So here cyclopropane is formed from this 1,3-dibromopropane. this cyclopropane is formed from here. What will happen? This from here, this Br will remove out from here, and this Br from remove out from here, and there are two molecule of the sodium is given here. So this sodium, after that there is a formation. There is a formation of the bond here between the CH2 and CH2, and there is a formation of the cycloalkane or your cyclopropane, and this Br2 will react with this Na. That is why there is a formation of this 2NaBr. So here 2NaBr is formed. Next is your from calcium or barium salt of dicarboxylic acid. So here when the calcium or barium salt of adipic, pimelic or subric acid is heated, a cyclic ketone is formed. A cyclic ketone is formed. So cyclic ketone may be readily converted into the corresponding cycloalkanes by means of the Clemmensen reduction. So here the process that is used, that is your Clemmensen reduction, and in this case when this calcium or barium salt, this calcium or barium salt of adipic, this is your barium adiphate, this is your barium adiphate. So these adipic, pimelic or summaric acid salt are heated. A cyclic ketone is formed. So this is here a cyclic ketone is formed there. And cyclic ketone may be readily converted into the corresponding cyclohexane by means of Clemmensen reduction. So firstly, this this salt of this adipic acid or the pimelic acid or your subric acids, these are converting, or these are converting into, when they are heated, they are converting into your ketone. So this is, there is a formation of this ketone. This is your cyclopentanone. So this cyclopentanone is formed here from this salt of the acid. When the salt of the acid is heated, then this cyclopentanone is formed here. That is your ketone. After that, and there is a formation of the barium carbonate. This, from here you will see that this, both of this carbon will attach to one of the CO, and here from here this CO3 will remove out from here. This CO3 will react with this barium. So barium carbonate is formed here, and then this cyclopentanone. This cyclopentanone is then reacted here, the Clemmensen reduction. This reaction is known as Clemmensen reduction. The reduction is occurring. So here, so in the reduction there is a addition of hydrogen, removal of oxygen. So here by treating this cyclopentanone or a ketone with this zinc amalgam or the HCl, there is a formation of a cycloalkane. So here you will see this is your this is your pentanone, this is your ketone, and there is a removal of this hydrogen, and this removal of this oxygen is removing out, and the hydrogen is adding. That is why this is your reduction, and this reduction is known as Clemmensen reduction. From this, the cyclic ketone is converting to the cyclopropentane in the presence of this zinc mercury HCl. Okay, so these are the this is the two methods. First is a dihalogen compound. Second is your calcium barium salt of dicarboxylic acid. And in this first, there is a dihalogen. When we are treating the dihalogen with the sodium or the ethanol, there is a formation of the cyclopropane. And in the second, we are using the barium or the calcium salt of dicarboxylic acid or an acid, that is a calcium or barium salt of adipic, phenolic or subric acid is heated. A cyclic ketone is formed. In this, they are converted to the corresponding cycloalkanes, and here this cycloalkane, this dicarboxylic acid is first converted into your this ketone. After that, this ketone is converted into the is reduced to your this cyclopentane. The next reaction is your from esters of dicarboxylic acid. So this is known as Dickman reaction. This is also known as Dickman reaction. So in this, the diesters, in that we have used the dicarboxylic acid, but here we are using this esters of this dicarboxylic acid. So here the diesters of adipic, phenolic or subric acid, when subric acid is treated, when treated with the sodium, undergoes intermolecular acetoacetic ester condensation. So here the acetoacetic condensation reaction is going and a ketoester is formed. So then the ketoester that is formed on hydrolysis, it is giving cyclic ketone. After that, the cyclic ketone again is reduced in the cycloketone by the mentioned reduction reaction. So here you will see this this is your diethyl adipate. This is your diethyl adipate, which is your ester of the carboxylic acid, because here you can see here this group is this R is attached to this COO. So this is the esters. This functional group is known as your esters, and when this ester is treating with this sodium, this is your dicarboxylic ester and diester, or you can say the diesters also. This diester is treated with this sodium. So here the sodium, when it is treated with the sodium, there is a removal of this salt of the ethane. So here ethyl salt is removed, so here you will see that this whole this is removing out from here. This is removing out from here, and if this is removing out from here, you can see the COO. See this CO. This CO, when this is removed out from here, this CO from this CO, this will form a bond. And here from here, one H is also removed out from. So there is a formation of this. This is what this is formed. This is a ketoester. This is a ketoester. This is a ketoester is formed. Ketoester is formed because here a keto group is attached and one ester group is also attached. That is why it is known as ketoester group is attached. This is your ketoester is formed here. After that, this ketoester is then hydrolysis in the presence of this aqueous HCl, and there is a formation of this. What is here formed? This cyclic ketone is formed here, plus here this carboxylic acid is formed here. After that, this ketoester is hydrolyzed, or this is decarboxylated. Here decarboxylation reaction is occurring, and here you will see this CO2. This whole will remove out from here, and this H will go and attach to this CH2. So there is a formation of this ketone, and this ketone will reduced or will be reducted, and in the presence of zinc amalgam, and there is a formation of this cyclopentane. So here there is a formation of this cyclopentane. So how this cyclopropane is this cycloalkane is formed. Next is your fourth, from aromatic compounds. So benzene may be catalytically hydrogenated at elevated temperature and pressure to yield cycloalkane. So here you will see this benzene is reacting with this hydrogen, and there is a formation of this cyclohexane. So this cyclohexane is formed from this benzene in the presence of this hydrogen. Means hydrogenation is occurring with this benzene. Hydrogen is adding to this benzene, and this double bond is breaking, and this double bond is converting to this single bond compound. This is your cycloalkene side compound, and this is formed from this cycloalkene. This is converted to the cyclohexane. Unsaturated compound is converted to the saturated compound in the presence of this nickel, and also we are applying heat and the pressure. And next is your Fewed method. So in this Fewed method, terminal dihalides when treated with sodium or zinc form cycloalkane, and this reaction is an extension of Booth's reaction and useful for the preparation of 3,6 membered ring. So here the same, that is from the dihalo compound. Here also this halogens are removing in the presence of the sodium, and there is a formation of this cyclopropane is formed here. And this is an extension of a Booth's, because in this Booth's reaction also the halogens are removed out, and they are forming a bond with this sodium. So this is an extension of Booth's reaction. So here you will take the example. Here we have taken the example of 1,3-dichloropropane, and in this 1,3-dichloropropane is treated with the sodium, and from this the chlorine will remove out from here, and there is a formation of sodium chloride, and there the bond between the CH2 will form, and this is a cyclopropane is formed here. Next is your Bicillison Sinus method. So in this, from calcium or barium salt of dicarboxylic acid, this is formed. So the calcium salt Here it is removed out, then ketone is formed, and the ketone is then pre-mentioned reduction, and this is your cyclobutane is formed. Next is your carbenes. So here carbenes are highly reactive carbon species, and they add to alkene to form cyclopropane derivative. And carbenes, being highly reactive intermediate, it cannot be isolated. Hence, reactions carried out with reacting alkene with compound generating carbene. So here you have seen that here it is written, here it is given a reaction that 2-butene is treated with this this carbene is reacting with this CH2NH2, and there is a formation of this cyclopropane is formed here. Because here from this the nitrogen is removed out from here, and that CH2 will get attached to that butene. So next is your from diol-allyl reaction. So in this diol-allyl reaction, the cycloaddition of conjugated dienes and dienophils to give cyclic compound is called diol-allyl reaction. And this we have already studied in that cyclohexane. In the in your which topic, alkene. So in this dienes, we conjugated diene. So this 1,3-dibutadiene is a conjugated diene, and when it is treated with this dienophil at 473 Kelvin, then there is a formation of this cyclohexane, which will get reduced, and there is a formation of the cyclo group. The cyclo compound is formed here, and cyclohexane is formed here. Next is your hydrogenation of benzene ring. So cyclohexane may be formed by hydrogenating compound with benzene ring, many of which are isolated from coal, as illustrated with toluene. So when this toluene, which is isolated from this coal, is hydrogenated, then there is a formation of methyl cyclohexane. So this is the same reaction that benzene. When benzene is also hydrogenated, there is a formation of the cyclo compound. So in this also, this is also a benzene benzene compound. So here toluene, when it is hydrogenated, there is a formation of a cyclo compound. Next is the chemical reaction. So in this chemical reaction, the cycloalkanes react mostly like they're corresponding to the straight chain alkane and halogenation in presence of UV light. So they produces more substituted halogen without breaking the ring. So cyclopropane plus chlorine in the presence of your UV light, there is a formation of this cyclopropane. And here the same cyclobutane is given, and then cyclobutane is brominated in the presence of UV light. There is a formation of this bromocyclobutane is formed. Next is the addition of chlorine and bromine in presence of carbon tetrachloride in dark. So here cyclopropanes react with chlorine, bromine at room temperature, and in the absence of diffuse sunlight to produce 1,3-cyclo dichloropropane and 1,3-bromo cyclopropane. And one of the carbon-carbon bond of cyclopropane is broken, and the 2 halogen atom appear at the end of the propane chain. So this is the reversible of that reaction, that is the dihalogen. So here they are, this is a cyclo compound. It is treated with this halogen, dihalogen, in the presence of the dark and in the presence of this carbon tetrachloride, and there is a formation of this open chain, and 1,3-dichloropropane is formed there. And in the same case, there's bromo. When this bromo is reacted with this cyclopropane, then there is a formation of this 1,3-dibromopropane. Next is a reaction with concentrated HBr and IHI. So here, when this is reacted with this HBr, the hydrogen bromides, and they produces 1-bromopropane. And when they are reacted with this hydrogen iodide, they form 1-idopropane. Next is the addition of hydrogen catalytic reduction. So here the catalytic reduction is occurring, means here the addition of hydrogens are occurring, and when there is a addition of hydrogen is occurring, then there is a breakage in this bond, and there is a formation of this propane or the N-butane. Means from the ring they are forming a straight chain. Next are the questions. So identify the incorrect statement regarding cycloalkane. So it is the hydrophilic hydrocarbon. Cycloalkane exhibit aromatic character, they fall. Identify the incorrect statement regarding cycloalkane. So this is they occur in gaseous form in nature. So identify the compound with the highest ring strain, that is your A, cyclobutane. Which among the following compound explode on contact with oxygen, that is your cyclobutane. Identify the E-cyclic hydrocarbon, which is highly flammable, that is your B-cyclopentane. So these are the references from where we can study this topic, that is a cycloalkane. And thank you so much for today's lecture.